Hey kids, welcome to doing some multivariable by video. So what I did for Stokes Theorem day 3 was get a bunch of University of Maryland um, problems involving Stokes Theorem and their rubrics. I've attached the problems to the email message that I sent you, and I'm going to do 3 of them with you here on video and then leave you to do 3 yourself. So University of Maryland, their rubrics, they always do Stokes Theorem problem the same way, where they parametrize the surface. They go from a line integral to a double integral of curl f dot n, and they always parametrize the surface. It doesn't have to be done that way, but at least I want to show you their technique. So how they state these problems, they give you orientation in the problem, so counterclockwise orientation when viewed from above. So you're looking down on this surface. Counterclockwise means, the orientation means I'm going to leave my answer. I'm not going to have to negatize anything. They want me to apply Stokes theorem to the line integral. That's my cue that I want to do double integral of curl f dot n. But they want me to parametrize the resulting surface. I don't believe you have to. Kids have not done this. They told me in the past, and they've still gotten credit for their exams, but for these problems. But again, I don't see the problem or the grades. So just wanted to make sure that you have exposure to the way they write their rubrics. And notice I don't have to evaluate this integral, but they ask me to keep going until I have an iterated double integral. And what they mean by that is they want to see the double integral with limits on both integral sides. So I make note of my orientation. I'm going to calculate the curl over the surface. So the line, I can see in the line integral what my force field is, x, y, and z directions. So there's my force field. Set up my curl determinant. Take a moment, see what you get out of that. I got a nice one, 0, negative z, and y. So here's where they differentiate from us. Instead of doing that negative p del z del x, blah, 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 they always parametrize the surface. And we do a trivial one. X is going to be x, y is going to be y. And in this case, the reason I chose that was because z is in terms of both x and y. And remember, for a double integral, I only can have 2 variables. But I do feel a little bit chilly because I notice that my surface has a cylinder and a paraboloid. So I'm thinking maybe I won't make x x. Maybe I'll make x r cosine theta, y r sine theta, and z in terms of r and theta. So there's my position vector. R cosine theta, r sine theta, 9 minus r squared. That gets me to my surface, right? So that's the surface of the hat. We're not doing the brim, we're doing the surface. But the brim, remember, is still containing our surface. So now I'm going to calculate the normal to the surface. Calculating the normal means that I'm going to, and I'll try to draw this poorly, I'm sure. Over on my surface, if I've got, some little teeny parallelogram here and I'm finding the curl, and then I'm going to nail the curl down with its normal. I'm going to do that everywhere. I'm going to find the circulation, dot it with the normal. So to find the normal, I have to do my little change in r and my little change in theta for every time I go out to that point, right? Every time I radiate, my position vector gets me out to that surface. So partial r with respect to r, partial r with respect to theta. Here's my normal, the cross product of those two, right? In that plane, I'm going to get a perpendicular vector that nails it down to the surface. And there's my cross product. So now I just need to take my curl of f here, noticing that my curl is not in the appropriate variables yet. So I need to take my curl and I need to take my normal. So I restated my curl, restated my normal, and I'm going to use Stokes now to rewrite the line integral as curl f dot n. So there's my curl f dot n. I filled in my n and made note that my curl needs to be in terms of how I defined z and y. And I'm going to do the dot product of those, right? The dot product, how much is the circulation in line, right, with the force? That's what the dot product is telling us. And then I just have to think about the brim and my boundary, right? To find all these, sum up all these curls. I need to go from, right, 0 to 3 and all the way around 0 to 2 pi. Right, and so doing my dot product, obviously my 0 makes that go away. And then I did negative 9r squared here and r sine theta there, added them together, and my two variables are dr and d theta. Notice there's no need for a Jacobian because I write my normal vector, my changes, my tangents were all already in terms of r. My position vector was in terms of r, and my tangents were in terms of r. And then when I crossed them, I got my normal. So I don't need the r, dr, d theta, right? I just need to list the two variables that I'm doing for my double integral. All right, congratulations. So that's the first one. Number 3. So again, the handout has number 2. I'm skipping a number 3 on the handout. Try to get a different, little different look for each one of these. So this time I have the intersection of a plane with a cylinder. And the cylinder is in terms of y and z. I have counterclockwise orientation, so I'm thinking, leave my integral alone. When viewed toward the origin from way out on the positive x-axis, so that's here, right? So you're like standing way out here and you're looking down and you're seeing counterclockwise rotation. And they want me to apply Stokes theorem to a line integral, right? And proceed until I have an iterated double. And once again, they're not asking me to evaluate it. So I make note my orientation, so I don't have to change the sign of my resulting answer. I'm going to find the curl, right? The curl is the x, y, and z from the line integral, x component, y component, z component. Set up my curl determinant. Take a moment. And that's what I got. Now doing the surface parametrization, notice this time, since I had my y and z was how my parameter was defined, I did my trivial parametrization, leaving y in terms of y, z in terms of z, but getting x by itself. Notice I felt a little chilly because, again, I have that cylinder. So I said I'm going to write x in terms of r and theta. Y is then my y and z are then my circular cosine and sine piece. So the plane getting x by itself was 12 minus 3y, right? So that's where I got this from. This was 12 minus 3y, x equals, and then I just used my replacement for y. And then here's my y, r cosine theta, and r sine theta. Now I'm going to do my partials to get the normal. So how do I, little teeny movement with respect to r, little teeny movement with respect to theta, cross them to get my normal. Take a moment. That's what I got. Love when I get a 0, right? Love that situation. So just combined everything, my orientation, my curl, my normal. They gave me a line integral. They asked me to use Stokes to find the double integral that would give me the same result. So there's my curl. I put in my n, but notice that I've got to change my x and my y's. So x, remember, was equal to 12 minus 3y, and this is 1 minus y, and this is 2 times x. Now what's nice is that since I'm dotting this and I've got a 0, I know this part 0 over there in the z position, I know that this part is just going to go away, right? So I just had to dot negative r with 12 minus 3r sine theta and negative 3r with negative r cosine theta. And then once again, the two variables that I were using was integrating with respect to r, and the little change in the r, little change in the theta, that's my dA. And my radius was 2, and I was going all the way around. All right, one more. Number 5. So let sigma there, that's that University of Maryland loves to call their surfaces, that sigma, be part of the vertical plane in the first octant below z equals 5. So this time I've got clockwise orientation when viewed from the first octant, looking down towards or looking over towards the origin. So consider a line integral, use Stokes. So notice the pattern, right? Got two things intersecting, creating a brim and a hat. There, they give me the line integral around the brim. They tell me about orientation, and they ask me to use Stokes. And then they tell me I don't have to integrate. So here's my orientation clockwise. Curl again, I got from my line integral. There's my curl determinant. Go ahead and calculate that. Tell me what you get. That's what I got. Now I'm going to parametrize the surface. Once again, my plane, right? I could get x in terms of y and z. So I wrote my position vector and then found my normal. Notice this time I didn't feel any chill, right? I'm in a first octant. I've got a top of a, right? I've got a plane capping, one plane in the z capping this other plane coming down and slicing through from the top. I don't feel cold. I've got a bunch of triangular situation and rectangular situations going on. So I just took the little movement in y and the little movement in z, crossed them. This is a nice cross product, isn't it? Set up my double integral. I curl F. Curl F. Nail down each little circulation piece with its normal. Dot them. And then dA is going to be my y and my z. My y's went away. I just have 4z. And then, of course, the problem gave me that my y was between 0 and 2, and my z was up to 5, right? So 0 to 5. Notice that I negated the double integral because of my orientation was clockwise. Right? All right, so there's those 3 problems. Again, the handout has 3 more problems for you to try. See if you can do them all in the UMD style. And then again, I don't believe that there is any requirement that you must do it this way, but it's always good to see a different way of doing it. And plus, like the rubrics that I will share with you, you can see that that's how they always do them.